Relativity, the Special and General Theory. A popular exposition by Albert Einstein, PhD, Professor of Physics in the University of Berlin. Authorized translation by Robert W. Lawson, DSc, University of Sheffield, 1916.
The present book is intended as far as possible to give an exact insight into the theory of relativity to those readers who, from a general scientific and philosophical point of view, are interested in the theory, but who are not conversant with the mathematical apparatus of theoretical physics. The work presumes a standard of education corresponding to that of a university matriculation examination, and despite the shortness of the book, a fair amount of patience and force of will on the part of the reader. The author has spared himself no pains in his endeavor to present the main ideas in simplest and intelligible form, and on the whole in the sequence and connection in which they actually originated.
In the spirit of clearness, it appeared to me inevitable that I should repeat myself frequently, without paying the slightest attention to the elegance of the presentation.
I adhere scrupulously to the precept of that brilliant theoretical physicist Albert Einstein, according to whom matters of elegance ought to be left to the tailor and to the cobbler. I make no pretense of having withheld from reader difficulties which are inherent to the subject. On the other hand, I purposely treated the empirical physical foundation of the theory in a step-motherly fashion, so that reader unfamiliar with physics may not feel like the wanderer who was unable to see the forest for the trees. May the book bring someone a few happy hours of suggestive thought.
Chapter number 1. Physical meaning of geometrical propositions. In your school days, most of you who read this book made acquaintance with the noble building of Euclid's geometry, and you remember, perhaps with more respect than love, the magnificent structure on the lofty staircase of which you were chased about for uncounted hours by conscientious teachers. By reason of our past experience, you would certainly regard everyone with disdain who should pronounce even the most out-of-the-way proposition of this science to be untrue. But perhaps this feeling of proud certainty would leave you immediately if someone were to ask you, what then do you mean by the assertion that these propositions are true? Let us proceed to give this question a little consideration. Geometry sets out from certain conceptions such as plane, point, and straight line, with which we are able to associate more or less definite ideas, and certain simple propositions, axioms, which, in virtue of these ideas, we are inclined to accept as true. Then, on the basis of a logical process, the justification of which we feel ourselves compelled to admit, all remaining propositions are shown to follow from these axioms. That means they are proven. A proposition is then correct, true, when it has been derived in the recognized manner from the axioms. The question of truth of the individual geometrical propositions is thus reduced to one of the truth of the axioms. Now, it has long been known that the last question is not only unanswerable by the methods of geometry, but that it is in itself entirely without meaning. We cannot ask whether it is true that only one straight line goes through 2 points. We can only say that Euclidean geometry deals with things called straight lines, to each of which is ascribed the property of being uniquely determined by 2 points situated on it. The concept true does not tally with the assertions of pure geometry, because by the word true, we are eventually in the habit of designating always the correspondence with real object. Geometry, however, is not concerned with the relaxation of ideas involved in it to objects of experience, but only with the logical connection of these ideas among themselves. It is not difficult to understand why, in spite of this, we feel constrained to call the propositions of geometry true. Geometrical ideals correspond to more or less exact moments in nature, and these are undoubtedly the exclusive cause of the genesis of those ideas. Geometry ought to refrain from such a course, in order to give to its structure the largest possible logical unity. The practice, for example, of seeing in a distance 2 marked positions on a practically rigid body is something which is lodged deeply in our habit of thought. We are accustomed further to regard 3 points as being situated on a straight line, if their apparent positions can be made to coincide for observation with one eye under suitable choice of our place of observation. If, in pursuance of our habit of thought, we now supplement the propositions of Euclidean geometry by the simple propositions that 2 points on a practically rigid body always correspond to the same distance, line interval, independently of any changes in position to which we may subject the body, the propositions of Euclidean geometry then resolve themselves into propositions of the possible relative positions of practically rigid bodies. Note of the translator: it follows that a natural object is associated with a straight line. 3 points A, B, and C on a rigid body thus lie in a straight line when the points A and C being given, B is chosen such that the sum of the distances A and B and BC is as short as possible. This incomplete suggestion will suffice for the present purpose. Geometry, which has been supplemented in this way, is then to be treated as a branch of physics. We can now legitimately ask as to the truth of geometrical propositions interpreted in this way, since we are justified in asking whether these propositions are satisfied for those real things we have associated with the geometrical ideas. In less exact terms, we can express this by saying that by the truth of a geometrical proposition in this sense, we understand its validity for a construction with rule and compasses. Of course, the conviction of the truth of geometrical propositions in this sense is founded exclusively on rather incomplete experience. For the present, we shall assume the truth of the geometrical propositions, then at a larger scale, then at a larger stage. In the general theory of relativity, we shall see that this truth is limited, and we shall consider the extent of its limitation. End of chapter. Chapter number 2. The system of coordinates. On the basis of the physical interpretation of distance, which has been indicated, we are also in a position to establish the distance between 2 points on a rigid body by means of measurements. For this purpose we require a distance, rod S, which is to be used once and for all, and which we employ as a standard measure. If now A and B are 2 points on a rigid body, we can construct the line adjoining them according to the rules of geometry. Then, starting from A, we can mark off the distance S time after time until we reach B. The number of these operations required is the numerical measure of the distance AB. This is the basis of all measurement of length. Here we have assumed that there is nothing left over. That means the measurement gives a whole number. This difficulty is got over by the use of divided measuring rods, the introduction of which does not demand any fundamentally new method. Every description of the scene of an event or of the position of an object in space is based on the specification of the point on a rigid body of reference, with which that event or object coincides. This applies not only to a scientific description, but also to everyday life. If I analyze the place specification Times Square, New York, I arrive at the following result. The Earth is the rigid body to which the specification of place refers. Times Square, New York, is a well-defined point to which a name has been assigned and with which the event coincides in space. Translator note: Einstein used Potsdamer Platz, Berlin in the original text. In the authorized translation, this was supplemented with Trafalgar Square, London. We have changed this to Times Square, New York, as this is the best known location to English speakers in the present day. Additionally, it is not necessary here to investigate further the significance of the expression coincidence in space. This conception is sufficiently obvious to ensure that differences of opinion are scarcely likely to arise as to its applicability in practice. The primitive method of space specification deals with places on the surface of rigid bodies and is dependent on the existence of points on this surface which are distinguishable from each other. But we can free ourselves from both of these limitations without altering the nature of our specification of position. If, for instance, a cloud is hovering over Times Square, then we can determine its position relative to the surface of the Earth by erecting a pole perpendicularly on the square, so that it reaches the cloud. The length of the pole measured with the standard measuring rod combined with the specification of the position of the foot of the pole supplies us with a complete place specification. On the basis of this illustration, we are able to see the manner in which a refinement of the conception of position has been developed. We imagine the rigid body to which the place specification is referred, supplemented in such a manner that the object whose position we require is reached by the completed rigid body. In locating the position of the object, we make use of a number, here the length of the pole measured with the measuring rod, instead of designated points of reference. We speak of the height of the cloud, even when the pole which reaches the cloud has not been erected. By means of optical observations of the cloud from different positions on the ground, and taking into account the properties of the propagation of light, we determine the length of the pole we should have required in order to reach the cloud. From this consideration, we see that it will be advantageous if, in the description of position, it should be possible by means of numerical measures to make ourselves independent of the existence of marked positions, possessing names, on the rigid body of reference. In the physics of measurement, this is attained by the application of the Cartesian system of coordinates. Or should I say Cartesian or Cartesian system of coordinates. This consists of three plane surfaces, perpendicular to each other and rigidly attained to a rigid body, referred to as system of coordinates. The scene of any event will be determined by the specifications of the lengths of the three perpendiculars or coordinates x, y, z, which can be dropped from the scene of the event to those three plane surfaces. The lengths of these three perpendiculars can be determined by a series of manipulations with rigid measuring rods, performed according to the rules and methods laid by Euclidean geometry. In practice, the rigid surfaces which constitute the system of coordinates are generally not available. Furthermore, the magnitudes of the coordinates are not actually determined by constructions with rigid rods, but by indirect means. If the results of physics and astronomy are to maintain their clearness, the physical meaning of specifications of position must always be sought in accordance with the above considerations. Clarification of the translator. A refinement and modification of these views does not become necessary until we come to deal with the general theory of relativity, treated in the second part of this book. We thus obtain the following result. Every description of events in space involves the use of a rigid body to which such events have to be referred. The resulting relationship takes for granted that the laws of Euclidean geometry hold for distances, the distance being represented physically by means of the convention of two marks in a rigid body. End of chapter. Chapter number 3. Space and time in classical mechanics. The purpose of mechanics is to describe how bodies change their position in space with time. I should load my conscience with grave sins against the sacred spirit of lucidity, were I to formulate the aims of mechanics this way, without serious reflection and detailed explanations. Let us proceed to disclose these sins. It is not clear what is to be understood here by position and space. I stand at the window of a railway carriage which is traveling uniformly, and dropped a stone on the embankment without throwing it. Then, disregarding the influence of the air resistance, I see the stone descend into a straight line. A pedestrian who observes the misdeed from the footpath notices that the stone falls to earth in a parabolic curve. I now ask, do the positions traversed by the stone lie in reality on a straight line or on a parabola? Moreover, what is meant here by motion in space? From the considerations of the previous section, the answer is self-evident. In the first place, we entirely shun the vague word space, of which we must honestly acknowledge we cannot form the slightest conception, and we replace it by motion relative to a practically rigid body of reference. The positions relative to the body of reference, railway carriage or embankment, have already been defined in detail in the preceding section. If, instead of body of reference, we insert system of coordinates, which is a useful idea for mathematical description, we are in a position to say, the stone traverses a straight line relative to a system of coordinates rigidly attached to the carriage, but relative to a system of coordinates rigidly attached to the ground embankment, it describes a parabola. With the aid of this example, it is clearly seen that there is no such thing as an independently existent trajectory, literally a path curve, but only a trajectory relative to a particular body of reference. Note of the translator, that is, a curve along which the body moves. In order to have a complete description of the motion, we must specify how the body alters its position with time. That is, for every point in the trajectory, it must be stated at what time the body is situated there. This data must be supplemented by such a definition of time. In virtue of this definition, these time values can be regarded essentially as magnitudes, results of measurements, capable of observation. If we take our stand on the ground of classical mechanics, we can satisfy this requirement for our illustration in the following manner. We imagine two clocks of identical construction. The man on the railway carriage window is holding one of them, and the man on the footpath the other. Each of the observants determines the position of his own reference body occupied by the stone at each tick of the clock he is holding in his hand. In this connection, we have not taken account of the inaccuracy involved by the finiteness of the velocity of propagation of light. With this, and with a second difficulty prevailing here, we shall have to deal in detail later. End of chapter. Chapter number 4. The Galilean System of Coordinates. As is well known, the fundamental laws of the mechanics of Galilei Newton, which is known as the law of inertia, can be stated thus. A body removed sufficiently far from other bodies continues in a state of rest, or of uniform motion in a straight line. This law not only says something about the motion of the bodies, but it also indicates the reference bodies or system of coordinates, permissible in mechanics, which can be used in mechanical description. The visible fixed stars are bodies for which the law of inertia certainly holds to a high degree of approximation. Now, if we use a system of coordinates which is rigidly attached to Earth, then, relative to this system, every fixed star describes a circle of immense radius in the course of an astronomical day, a result which is opposed to the statement of the law of inertia. So that if we adhere to this law, we must refer these motions only to systems of coordinates relative to which the fixed stars do not move in a circle. A system of coordinates of which the state of motion is such that the law of inertia holds relative to it is called a Galilean system of coordinates. The laws of the mechanics of Galilei Newton can be regarded as valid only for a Galilean system of coordinates. End of chapter. Chapter number 5. The principle of relativity in the restricted sense. In order to attain the greatest possible clearness, let us return to our example of the railway carriage supposed to be traveling uniformly. We call its motion a uniform translation. Uniform because it is of constant velocity and direction. Translation because although the carriage changes its position relative to the embankment, yet it does not rotate in doing so. Let us imagine a raven flying through the air in such a manner that its motion, as observed from the embankment, is uniform and in a straight line. If we were to observe the flying raven from the moving railway carriage, we should find that the motion of the raven would be one of different velocity and direction, but that it would still be uniform and in a straight line. Expressed in an abstract manner, we may say, if a mass M is moving uniformly in a straight line with respect to a coordinate system K, then it will also be moving uniformly and in a straight line relative to a second coordinate system K, provided that the latter is executing a uniform translatory motion with respect to letter K. In accordance with the discussion contained in the preceding section, it follows that if K is a Galilean coordinate system, then every other coordinate system K is a Galilean one, when in relation to k, it is in a condition of uniform motion of translation. Relative to k, the mechanical laws of Galilei and Newton hold good exactly as they do with respect to k. We advance a step further in our generalization when we express the tenet thus. If relative to k is a uniformly moving coordinate system devoid of rotation, then natural phenomena run their course with respect to k according to exactly the same general laws as with respect to k. This statement is called the principle of relativity in the restricted sense. As long as one was convinced that all natural phenomena were capable of representation with the help of classical mechanics, there was no need to doubt the validity of this principle of relativity. But, in view of the more recent development of electrodynamics and optics, it became more and more evident that classical mechanics affords an insufficient foundation for the physical description of all natural phenomena. At this juncture, the question of the validity of the principle of relativity became ripe for discussion, and it did not appear impossible that the answer to this question might be in the negative. Nevertheless, there are two general facts which at the outset speak very much in favor of the validity of the principle of relativity. Even though classical mechanism does not supply us with a sufficiently broad basis for the theoretical presentation of all physical phenomena, still we must grant it a considerable measure of truth, since it supplies us with the actual motions of the heavenly bodies with a delicacy of detail little short of wonderful. The principle of relativity must therefore apply with great accuracy in the domain of mechanics, but that a principle of such broad generality should hold with such exactness in one domain of phenomena, and yet should be invalid for another, is a priori not very probable. We now proceed to the second argument, to which, moreover, we shall return later. If the principle of relativity in the restricted sense does not hold, then the Galilean coordinate systems k, etc., which are moving uniformly relative to each other, will not be equivalent for the description of natural phenomena. In this case, we should be constrained to believe that natural laws are capable of being formulated in a particularly simple manner. And of course, only on condition that, from amongst all possible Galilean coordinate systems, we should have chosen one, KO, of a particular state of motion as our body of reference. We should then be justified, because of its merits for the description of natural phenomena, in calling this system absolutely at rest, and all other Galilean systems, K, in motion. If, for instance, our embankment were the system KO, then our railway carriage would be a system K, relative to which less simple laws would hold than with respect to KO. This diminished simplicity would be due to the fact that the carriage K would be in motion. Really, that means really, with respect to KO. In the general laws of nature which have been formulated with reference to K, the magnitude and direction of the velocity of the carriage would necessarily play a part. We should expect, for instance, that the note emitted by an organ pipe placed with its axis parallel to the direction of travel would be different from that emitted if the axis of the pipe were placed perpendicular to this direction. Now, in virtue of its motion, in an orbit around the Sun, our Earth is comparable with a railway carriage traveling with a velocity of about 30 km per second. If the principle of relativity were not valid, we should therefore expect that the direction of motion of the Earth at any moment would enter into the laws of nature, and also that physical systems in their behavior would be dependent on the orientation in space with respect to the Earth. For owing to the alteration in direction of the velocity of revolution of the Earth in the course of the year, the Earth cannot be at last relative to the hypothetical system KO throughout the whole year. However, the most careful observations have never revealed such anisotropic properties in terrestrial physical space. That means a physical non-equivalence of different directions. This is very powerful argument in favor of the principle of relativity. End of chapter. Chapter number 6. The theorem of the addition of velocities employed in classical mechanics. Let us suppose our old friend the railway carriage to be traveling along the railways with constant velocity v, and a man traverses the length of the carriage in the direction of travel with a velocity w. How quickly, or in other words, with what velocity w does the man advance relative to the embankment during the process? How quickly, or in other words, with what velocity w does the man advance relative to the embankment during the process? The only possible answer seems to result from the following consideration. If the man were to stand still for a second, he would advance relative to the embankment through a distance v equal numerically to the velocity of the carriage. As a consequence of his walking, however, he traverses an additional distance w relative to the carriage, and hence also relative to the embankment. In this second, the distance w being numerically equal to the velocity with which he is walking. Thus, in total he covers the distance w equals to v plus w relative to the embankment in the second considered. We shall see later that this result, which expresses the theorem of the addition of velocities employed in classical mechanics, cannot be maintained. In other words, the law that we have just written down does not hold in reality. For the time being, however, we shall assume its correctness. Chapter number 7. The apparent incompatibility of the law of propagation of light with the principle of relativity. There is hardly a simpler law in physics than that according to which light is propagated in empty space. Every child at school knows or believes he knows that this propagation takes place in straight lines with a velocity that is 300,000 kilometers per second. At all events, we know with great exactness that this velocity is the same for all colors, because if this were not the case, the minimum of emission would not be observed simultaneously for different colors during the eclipse of a fixed star by its dark neighbor. By means of similar considerations, based on observations of double stars, the Dutch astronomer De Sitter was also able to show that the velocity of propagation of light cannot depend on the velocity of motion of the body emitting the light. The assumption that this velocity of propagation of light is dependent on the direction in space is in itself improbable. In short, let us assume that the simple law of constancy of the velocity of light, c, in vacuum, is justifiably believed by the child at school. Who would imagine that this simple law has plunged the conscientiously thoughtful physicist into the greatest intellectual difficulties? Let us consider how these difficulties arise. Of course, we must refer the process of the propagation of light, and indeed every other process, to a rigid reference body coordinate system. As such a system, let us again choose our embankment. We shall imagine the air above it to have been removed. if a ray of light be sent along the embankment, we see from the above that the tip of the ray will be transmitted with the velocity c relative to the embankment. Now let us suppose that our railway carriage is again traveling along the railway lines with the velocity letter v, and that its direction is the same as that of the ray of light, but its velocity of course much less. Let us inquire about the velocity of propagation of the ray of light relative to the carriage. It is obvious that we can here apply the consideration of the previous section. Since the ray of light plays the part of the man walking along relatively to the carriage, the velocity w of the man relative to the embankment is here replaced by the velocity of light relative to embankment. W is the required velocity of light with respect to the carriage, and we have W equals c minus v. The velocity of propagation of a ray of light relative to the carriage thus comes out smaller than c. But this result comes into conflict with the principle of relativity set forth in section 5. For, like every other general law of nature, the law of transmission of light in vacuum, must, according to the principle of relativity, be the same for the railway carriage as a reference body as when the rails are the body of reference. But, from our above consideration, this would appear to be impossible. If every ray of light is propagated relative to the embankment with the velocity, letter c, then for this reason it would appear that another law of propagation of light must necessarily hold with respect to the carriage, a result contradictory to the principle of relativity. In view of this dilemma, there appears to be nothing else for it than to abandon either the principle of relativity or the simple law of the propagation of light in vacua. Those of you who have carefully followed the preceding discussion are almost sure to expect that we should retain the principle of relativity, which appeals so convincingly to the intellect because it is so natural and simple. The law of propagation of light in vacua would then have to be replaced by a more complicated law conformable to the principle of relativity. The development of theoretical physics shows, however, that we cannot pursue this course. The epoch-making theoretical investigations of H.A. Lawrence on the thermodynamical and optical phenomena connected with moving bodies show that experience in this domain leads conclusively to a theory of electromagnetic phenomena, of which the law of the constancy of the velocity of light in vacua is a necessary consequence. Prominent theoretical physicists were therefore more inclined to reject the principle of relativity, in spite of the fact that no empirical data have been found which were contradictory to this principle. At this juncture, the theory of relativity entered the arena. As a result of an analysis of the physical conceptions of time and space, it became evident that, in reality, there is not the least incompatibility between the principle of relativity and the law of propagation of light. And by systematically holding fast to both these laws, a logically rigid theory could be arrived at. This theory has been called the special theory of relativity to distinguish it from the extended theory, with which we shall deal later. In the following pages we shall present the fundamental ideas of the special theory of relativity. Chapter number 8. On the idea of time in physics. Lightning has struck the rails on our railway embankment at two places, A and B, far distance from each other. I make the additional assertion that these two lightning flashes occur simultaneously. If I ask you whether there is sense in this statement, you will answer my question with a decided yes. But if I now approach you with the request to explain to me the sense of a statement more precisely, you find after some consideration that the answer to this question is not so easy as it appears at first sight. After some time, perhaps the following answer would occur to you. The significance of the statement is clear in itself and needs no further explanation. Of course, it would require some consideration if I were to be commissioned to determine by observations whether in the actual case the two events took place simultaneously or not. I cannot be satisfied with this answer for the following reason. Supposing that as the result of ingenious considerations, an able meteorologist were to discover that the lightning must always strike the places A and B simultaneously, then we should be faced with the task of testing whether or not this theoretical result is in accordance with the reality. We encounter the same difficulty with all physical statements in which the concept simultaneous plays a part. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled with an actual case. We thus require a definition of simultaneity such that this definition supplies us with the method by means of which, in the present case, he can decide by experiment whether or not both the lightning strokes occurred simultaneously. As long as this requirement is not satisfied, I allow myself to be deceived as a physicist. And of course the same applies if I am not a physicist, when I imagine that I am able to attach a meaning to the statement of simultaneity. I would ask the reader not to proceed further until he is fully convinced on this point. After thinking the matter over for some time, you then offer the following suggestion with which to test simultaneity. By measuring along the rails, the connecting line AB should be measured up and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement, that means two mirrors inclined at 19 degrees, which allows him to visually observe both places A and B at the same time. If the observer perceives the two flashes of lightning at the same time, then they are simultaneous. I am very pleased with this suggestion, but for all I cannot regard the matter as quite settled, because I feel constrained to raise the following objection. Your definition would certainly be right, if only I knew that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M, but an examination of this supposition would only be possible if we already had at our disposal the means of measuring time. It would thus appear as though we were moving here in a logical circle. After further consideration, you cast a somewhat disdainful glance at me, and rightfully so, and you declare, I maintain my previous definition nevertheless, because in reality, it assumes absolutely nothing about light. There is only one demand to be made of the definition of simultaneity, namely that in every real case, it must supply us with an empirical decision as to whether or not the conception that has to be defined is fulfilled. That my definition satisfies this demand is indisputable. That light requires the same time to traverse the path A to M. As for the path B to M, is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. It is clear that this definition can be used to give an exact meaning not only to two events, but to as many events as we care to choose, and independently of the positions of the scenes of the events with respect to the body of reference, here the railway embankment. We suppose further that when three events A and B occur in different places in such a manner that A is simultaneous with B and B is simultaneous with C, simultaneous in the sense of the above definition, then the criterion for the simultaneity of the pair of events A and C is also satisfied. The assumption is a physical hypothesis about the propagation of light, it must certainly be fulfilled if we are to maintain the law of the constancy of the velocity of light in vacuo. We are thus led also to a definition of time in physics. For this purpose, we suppose that clocks of identical construction are placed at the points A, B, and C of the railway line, a coordinate system, in that they are set in such a manner that the positions of their pointers are simultaneously, in the above sense, the same. Under these conditions, we understand by the time of an event the reading position of the hands of that one of the clocks which is in the immediate vicinity in space of the event. In this manner, a time value is associated with every event which is essentially capable of observation. This stipulation contains a further physical hypothesis, the validity of which will hardly be doubted without empirical evidence to the contrary. It has been assumed that all these clocks go at the same time if they are of identical construction. Stated more exactly, when two clocks arranged at rest in different places of a reference body are set in such a manner that a particular position of the pointers of the one clock is simultaneous in the above sense with the same position of the pointers of the other clock, then identical settings are always simultaneous in the sense of the above definition. Chapter number 9. The Relativity of Simultaneity. Up to now, our considerations have been referred to a particular body of reference, which we have styled a railway embankment. We suppose a very long train traveling along the rails with the constant velocity v and in the direction indicated in figure number 1. People traveling in this train will, with advantage, view the train as a rigid reference body, a coordinate system. They regard all events in reference to the train. Then, every event which takes place along the line also takes place at a particular point of the train. Also, the definition of simultaneity can be given relative to the train in exactly the same way as with respect to the embankment. As a natural consequence, however, the following question arises. Are these two events, meaning the two strokes of lightning A and B, which are simultaneous with reference to the railway embankment, also simultaneous relative to the train? We shall show directly that the answer must be in the negative. When we say that the lightning strokes A and B are simultaneous with respect to the embankment, we mean the rays of light emitted at the places A and B where the lightning occurs meet each other at the midpoint M of the length A to B of the embankment. But the events A and B also correspond to positions A and B on the train. Let M be the midpoint of the distance A to B on the traveling train. Just when the flashes of lightning occur, this point M naturally coincides with the point M, but it moves towards the right in the diagram with the velocity v of the train. If an observer sitting in the position M in the train did not possess this velocity, then he would remain permanently at the point M, and the light rays emitted by the flashes of lightning A and B would reach him simultaneously, which means they would meet just where he is situated. Now, in reality, consider with reference to the railway embankment, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence, the observer will see the beam of light emitted from B earlier than he will see that one emitted from A. Observers who take the railway train as a reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. We thus arrive at the important result. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train, and vice versa. Relativity of simultaneity. Every reference body coordinate system has its own particular time, unless we are told the reference body to which the statement of time refers. There is no meaning in a statement of the time of an event. Now, before the advent of the theory of relativity, it had always tacitly been assumed in physics that the statement of time had an absolute significance, meaning that it is independent of the state of motion of the body of reference. But we have just seen that this assumption is incompatible with the most natural definition of simultaneity. If we discard this assumption, then the conflict between the law of the propagation of light in vacua and the principle of relativity developed in section 7 disappears. We were led to that conflict by the considerations of section 6, which are now no longer tenable. In that section, we concluded that the man in the carriage who traverses the distance w per second relative to the carriage traverses the same distance also with respect to the embankment in each second of time. But, according to the foregoing considerations, the time required by a particular occurrence with respect to the carriage must not be considered equal to the duration of the same occurrence, as judged from the embankment as reference body. Hence, it cannot be contended that the man in walking travels the distance w relative to the railway line in a time which is equal to 1 second as judged from the embankment. Moreover, the considerations of section 6 are based on yet a second assumption, which, in the light of a strict consideration, appears to be arbitrary, although it was always tacitly made even before the introduction of the theory of relativity. Chapter number 10. On the relativity of the conception of distance. Let us consider two particular points on the train traveling along the embankment with the velocity v and inquire as to their distance apart. That means the middle of the first and of the 100th carriage. We already know that it is necessary to have a body of reference for the measurement of a distance, with respect to which body the distance can be measured up. It is the simplest plan to use the train itself as a reference body, a coordinate system. An observer in the train measures the interval by marking off his measuring rod in a straight line. That means along the floor of the carriage, as many times as is necessary to take him from one marked point to the other. Then, the number which tells us how often the rod has to be laid down is the required distance. It is a different matter when the distance has to be judged from the railway line. Here, the following method suggests itself. If we call A and B the 2 points of the train, the 2 points on the train whose distance apart is required, then both of these points are moving with the velocity v along the embankment. In the first place, we require to determine the points A and B of the embankment, which are just being passed by the 2 points A and B at a particular time, t, judged from the embankment. These points A and B of the embankment can be determined by applying the definition of time given in section 8. The distance between the points A and B is then measured by repeated application of the measuring rod along the embankment. A priori, it is by no means certain that this last measurement will supply us with the same result as the first. Thus, the length of the train, as measured from the embankment, may be different from that obtained by measuring the train itself. This circumstance leads us to a second objection, which must be raised against the apparently obvious consideration of Section 6. Namely, if the man in the carriage covers the distance, W, in a unit of time, measured from the train, then this distance, as measured from the embankment, is not necessarily also equal